It's my absolute pleasure to be asked to chair this this first session of the talks given by Mark. And I thought I'd tell a story, which is not a very good story on my behalf, but goes back to the first time I met Mark, which was at MAM 2 in Winnipeg. I think that was the last time MAM was in Canada. And it was a great conference. And I went to every talk at that conference apart from one. One talk I did not go to was Mark's talk. And I was reliably told by a bunch of people who were there. I had a good reason, I was at a business meeting, but I was reliably told that I'd missed the best talk of the conference. And I not believe that was true, because it's not a mistake I've ever made again. At any conference where Mark's at, I have never missed his talk, and he invariably gives fantastic talks. And what I would say is that the sort of combination of energy that Mark brings, as well as innovative thinking, and the fact that you're sitting in IBM, Mark, so you get these sorts of interesting problems. So I've always found anything that Mark's had to talk about is highly stimulating, highly interesting. And we've got this title, which looks completely new, doesn't it? Entanglement, quantum computing, MAM, what more could you want? So I'm really looking forward to Mark's talk. Please, Mark.
Thank you. Thank you very much, Peter. And the check will be in the mail very soon. For my Canadian colleagues, I have a slightly revised title on the entanglement of matrix-analytic and quantum methods, eh? But what I'm going to be talking about, everybody that's not Canadian enjoyed that. The Canadians didn't enjoy that, and I apologize. What I'm going to talk about today will include aspects of a paper that Jose Blanchett, Mario Zegedi, Guanyang Wang, and I have written as a tutorial for the Winter Simulation Conference on quantum computing. So some of the background material will come from there. Some of the material that I'll be covering on the matrix-analytic methods and quantum computing algorithms is joint work with Vasilis Kalantis and Shashanka Rubu. Now, this talk is focused on or falls at the intersection of three different areas. One is stochastic processes and probability theory. The other is numerical analysis and methods. And the third is quantum computing. This will all be from a mathematical perspective. But the point is, I could literally spend 2 hours on each of these three areas. And since I only have 2 hours, since I only have an hour, what I'm going to try to do in all seriousness is I'm going to try to describe things in a way that those that are familiar with the area will get a deeper understanding, and those that are not familiar with that aspect will get an intuitive understanding. And I actually do want to go back and say one other thing, which is I want to thank the chairs first and foremost for this kind invitation. It's great to be here, and I really do appreciate it. I also want to thank them because I created, with my current situation, many more problems from them than they should have had to deal with. So in all sincerity, I truly do appreciate all the help and support that you've provided. With that said, let's start with a high-level introduction to quantum computing. I thought this might be helpful for those that maybe are not familiar. In 1980, Paul Benioff proposed a quantum version of a Turing machine, and he showed that such a device could be described using quantum mechanics. This was followed in 1981 by a conference on the physics of computation that was jointly sponsored by IBM and MIT, and both Benioff and Richard Feynman gave a keynote talk. In Feynman's keynote, in particular, he addressed the idea of simulating physics with computers, and he introduced the concept of a quantum simulator, a machine that, unlike a universal Turing machine, specializes in simulating quantum mechanical phenomena. And in fact, this talk, Feynman's talk, is often credited with actually kicking off the entire area of quantum computing. And of course, quantum computing has since evolved far, far beyond that. There is a very famous, or now famous, quote. It's actually the ending comment of Feynman's keynote, in which he said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. I'd like to suggest a corollary, which is quantum mechanics isn't deterministic, damn it. And if you want to make quantum computing efficient, you better make it mathematically probabilistic with some linear algebra, among other fields of mathematics. And by golly, it's a wonderful problem because it doesn't look so easy. There's another possible corollary of a famous quote by Einstein, but we won't get into that, although I will touch upon that a bit. So I'm going to, hopefully we can recall that the basic unit of information in classical computing is the binary bit, which takes on value 0 or 1. In quantum computing, the basic unit of information is a quantum bit or a qubit, which can exist in superposition. That means it actually exists simultaneously in two states. So it exists in the superposition of the basis state. This is notation that Paul Dirac invented, I guess one would say, or proposed. It's called ket. So ket 0 is just the state 0. Now states or qubits are actually column vectors in quantum computing. So ket 0 is the column vector 1, 0, and ket 1 or state 1 is the column vector 0, 1, and this is with complex amplitudes. So a qubit written here as this state, this qubit S, is equal to alpha 0 plus beta 1, where alpha and beta are complex, and they satisfy the absolute value of alpha squared plus the absolute value of beta squared equals 1. And in fact, well, I'll get down to that in a second. Now, these probability amplitudes can interfere constructively or destructively because they can be positive, negative, or complex numbers. And it's actually this notion of amplitude, probability amplitude, that plays an important role in this quantum interference that results from it. But the idea that's very different from a classical computer is when you measure a state or a qubit, you get a value, but then it collapses. It's no longer available. It no longer exists. When you're in a classical computer, you're asked to look at a particular bit. It's a 1 or a 0. You can look at it again. In quantum, you measure it and it collapses. And in particular, it collapses to state 0, or the value 0, if you will, with this probability that we have here, alpha, or the absolute value of alpha squared, and to state 1 with probability the absolute value of beta squared. Okay? So that was just a single qubit. More generally, when we have a quantum state, it's represented as a unit vector in a space of multiple qubits. Superposition, as I mentioned, is the notion that, or the condition in which a system can exist in multiple states simultaneously. Again, remember, I had that qubit S. I measured it. It gave me a 0 with probability a half, or alpha, the alpha, and the probability 1 with the probability associated with the beta. Once that happens, it no longer exists. But prior to my measuring it, it exists in both states because both are possible when you measure it. And oops, hit the wrong button. Now I see why other speakers have had difficulty. It's not that easy. So an n-bit qubit state is in C to the 2 to the tensor n, and the standard basis in general B sub n will be the set of all states of unitary vectors of length n. So for example, in the case of a qubit state, it's 2 to the 2, or 4 elements, and it's given by these 4 column vectors here. And since measurement, this is a key point, since measurements in quantum computing is probabilistic, quantum algorithms often require multiple runs, right? I told you that I measured it, I got a 0 with some probability, or 1 with a different probability. So you'll run the algorithm multiple times to get the distribution basically between 0 and 1. So, okay, so now we understand hopefully qubits to some extent. And now we're going to do operations on the states of n qubits. These states are vectors in 2 to the n complex Hilbert space. And the operations correspond to multiplication by 2 to the n by 2 to the n unitary matrices. These operations are represented in circuits, which are essentially gates. These gates are sort of the quantum analog of logical gates in a classical computer. And it's this exponentially large Hilbert space in which quantum computers are performed that creates significant speed up over classical algorithms. Now, let me mention one quick thing here. Peter and I were talking a second ago about quantum computing. So you have this exponential space, that's for the computation, but the pipe in and the pipe out is smaller. It's n. And so if it takes you an exponential amount of time to either load your problem in the quantum computer or get the results out of the quantum computer, then any exponential speed up you might get in the computation space is being wiped out. And this is what's happened. A lot of the early algorithms just focused on the computation and didn't focus on the input and the output. And so now there's been a pendulum swing in the other direction where people are almost maniacally focused on the input and output. And my view sometimes is, well, we still should try to see what we can do in the computation space, because maybe at some point people will figure out how we can do better jobs on the input and output. But that's just a side comment, which hopefully is not recorded. I'm joking. You may have seen these type of pictures, so I just want to sort of describe to you. Here we have 2 qubits. Oh, wait, sorry, 3 qubits. You know the story. There are 3 types of mathematicians, those that can add and those that can't. But here we have 3 qubits, Q0, Q1, Q2. And the main thing I just wanted to highlight was, you might see these diagrams and wonder what's going on. This is just saying that you have these qubits that are initialized in some way. This is a Hadamard gate or matrix, which we'll talk about in a second, and X, poly X, which we'll talk about. These represent measurements. So this is just describing how the algorithm is implemented on the quantum computer. It's a visual representation. So 3, as I mentioned, I mentioned some examples, but 3 important examples of the type of operators or matrices that are often used are the so-called poly X, which is just actually a NOT gate, poly Y, poly Z, which is a phase flip, represented here. And these matrices together with I form a basis for all 2 to the n Hermitian matrices. The Hadamard gate, which we saw a bit before, is represented this way, and it actually has a very nice, interesting feature. So this is just saying that the state at the qubit S is equal to the Hadamard applied to the state initialized to 0, and the result is this. And if you think about it for a second, what this is saying is that if I have any state that's initialized to 0, after I applied the Hadamard gate, the qubit now has a 50% chance of being 0 when measured and a 50% chance of 1 being measured, which again, if you think is 1 over the square root of 2 are your alpha and your beta. And so if you just do those calculations, you get a half. But an important point is that the state, until it's measured, is neither 0 nor 1. It's in a coherent superposition of both 0 and 1. You may have heard of Schrodinger's cat thought experiment, and that's sort of what he was getting at. An important property in the setting of quantum is entanglement. This is really a critically important property. I'm going to try to explain it here, and I'll make a connection to Einstein, and then I'll sort of, from a numerical analysis perspective, give you a better insight into what this is. But the basic idea is that quantum correlation, entanglement is a form of quantum correlation between different qubits. And that's the reason of the bad pun in my title on the entanglement between matrix-analytic methods and quantum computing. But remember, an n-bit quantum state can be expressed as a tensor product of n single qubit states. You'll remember that from the earlier chart that I had here, right? So an n qubit state is represented as a tensor product of the single qubit states. Otherwise, on the other hand, it's possible for n qubits to be in quantum states that cannot be expressed of tensor product of n single qubit states. And it's those states that cannot be represented as a tensor product of the n single qubit states that are called entangled states. And this really, the quantum mechanics bothered Einstein. He referred to it as spooky. And he wrote a paper with Podolsky and Rosen where he thought he was just demonstrating that quantum mechanics couldn't be right. There's something wrong. And I'll explain what that is. And it turned out that that spooky behavior is in fact a reality of quantum mechanics. There is no error. But just to give you an insight into the idea, the example of a two-bit quantum state where the state is 0, 0, or 0, or 1, 1, each with probability 1 over the square root of 2. Now, if you think about it, when you measure the first qubit of the state, you're going to get a 0 or a 1. Once you measure that, you know what the second qubit is. Because each of these happen with probability a half, there's no other possibility. So observe, the point is, if you measure the first qubit and you get a 0, then the state has to collapse to 0, 0, and similarly for the measurement of 1. So the property, the measurement of the first qubit immediately reveals the second qubit. This is the type of correlation that exists that one takes advantage of in developing quantum algorithms. So to better understand, now this is more from a numerical linear algebra perspective, maybe. Just think of what happens. We have an n qubit state S that an n qubit state S and an n prime qubit state S prime. That can be expressed by 2 to the n or 2 to the n prime complex numbers. The tensor product would be given in this way. And so the tensor product of these quantum states depend on 2 to the n plus 2 to the n prime complex numbers. But the quantum state in this joint space can actually be expressed by 2 to the n plus n prime complex numbers. So these are the ones that can be represented by, oh, come on. These are the ones that can be represented by tensor products. These are all the possible. So all the ones that cannot be represented by tensor products are called entangled states. And this is a really important aspect of quantum because and in fact, people have done measurements where they've actually over long distances have been able to show that this correlation really does exist. I also think this is interesting because it does reflect some of the difference between classical probability theory and quantum probability theory, if you will. So just quickly, superposition, things can be in the same state. Entanglement, form of correlation, very unlike what we get in classical. And again, it's because you have these tensor products that represent states, but these states, not all of them in the joint space that you're looking at can be represented as tensor products. Measurements will cause, you'll get the result, but it'll cause the state to immediately collapse with a given probability. Two things I didn't talk about, just so that you're aware. The no cloning theorem is that it's impossible to create a copy of an unknown quantum state in general. So in other words, in a computer, you can take a value and you can copy it. Quantum, you can't. So there's no notion of cloning. You need to recompute things. It's called the no cloning theorem. And an oracle is just a black box function that produces a particular output based upon a typical input. It's used a lot in quantum algorithms because it's just something that we know how to do. But instead of complicating the algorithm, we say there's an oracle that takes care of that part of the calculation. Okay, so now probability theory and stochastic processes. I think many of the people in the audience are going to be familiar with a lot of the stuff here, but I do want to go through it and make sure that we're all on the same page. So we're looking at structured Markov processes. Consider discrete time, continuous time would follow similarly, but we're continuing a discrete time structured Markov process on the two-dimensional state space where I is the levels. Many people have already described this, so I don't need to describe it as much. And I is the levels and J is the phase. The matrix for the so-called MG1 type process is given in this way. So it's called skip free to the left. You can only go one level back, but you can do jumps, as many jumps as you like forward. The GM1 is the other way around. You're skip free to the right. You can only go to the right one level, but you can go back as many levels. Hopefully this is already clear, but this is what I was saying, that the A1 goes forward one from I, and A2 goes two levels. It goes from I to I plus 2, and so on, similarly going backwards. And A0 is transitions within the level. For those that aren't familiar with this, the reason this is called an MG1 type is that Markov processes embedded at certain completion epochs for the classical MG1Q have the form of this matrix, and similarly for the G of 1. And birth-death processes are at the intersection where you just have the tri-diagonal structure. Our goal is to obtain the stationary distribution, not to solve the Markov process, but to obtain the stationary distribution. Define the stationary distribution here. Again, we partition it based upon the levels. The pi is the limiting probability vector pi is the stationary distribution. I'm going to assume throughout that the process is irreducible and ergodic, and its invariant probability vector therefore exists, and is determined by solving pi equal pi p, or for my Greek friends, p equal pp, and then normalizing it with the 1. Given the stationary distribution, you can compute various measures of interest related to levels and phases, which other people have described. Okay, so there's two primary forms of mathematical analysis to determine the stationary distribution. One near and dear to my heart, and Amir mentioned it in his talk, analytical approaches. In fact, the paper that Amir mentioned, we have a follow-on paper to that actually generalizes things. And this is an area that I really think is rich and very interesting. But the second area is computational approaches, and that's what I'm going to be focusing on here. There's been a lot of work in the classical computing context, but to our knowledge, there's no corresponding research in the quantum computing context. And our goal is to speed up the best known classical computational algorithms by devising quantum algorithms to essentially the bottlenecks, the most expensive parts of the classical computer, the classical algorithm get executed on the quantum computer. We're not doing everything on the quantum computer. It's just the bottlenecks. You can think of it as, people use GPUs to speed up certain computations as part of a larger algorithm. We're doing similar things here, where instead of a GPU, it's a QPU, a quantum processing unit. Now, there's an important duality between MG1 type processes and GM1 type processes. I won't get into that, but my point is, because of that, we're just going to focus on the MG1 type. So keep this picture in mind. We're going to be focusing on this class of matrices. And the key to the analysis, which again, many of the people here already know, the key of the analysis to obtain the stationary is to solve for the minimal non-negative solution of the matrix 2 in equation 2. So just to break this down, let's define theta L to be the first entry time into level L. Remember, levels are the first component. So if you think of it as a two-dimensional lattice, it's the one that all the states that have the same value I for different phase values. Now, I think Amir described the probabilistic interpretation or description of the matrix R. We're going to focus on the G matrix for reasons that will become clear. And the J sub I, forget about the I for a second. The J sub kth element of G denotes the probability that if you start in some level I plus L and phase J at time 0, so it's the probability that when you enter level L, starting from this level I plus L, for the first time and in finite time, you enter the state LK. Okay, so you start in I plus L at time 0, and the first time you enter level L, it's by entering phase K of level L. So that's the notion for, and this I here, it just actually holds for all L. So it can be for any I, but it doesn't matter what L is, given the structure. And so these are known results that I'm just going to mention. In particular, the stationary distribution is given by known theoretical results with respect to a matrix G min. And the results follow from a couple of, a lemma and a couple of theorems that I'm going to present. One is that we have this expression here, these G sup I form minimal non-negative solutions of this equation here, according to an element-wise ordering, and H is going to play an important role. So we'll see this again. This theorem A2 here actually gives us the G min as the minimal non-negative solution of that equation 2, where G sup I is actually the ith power of G min. That's the G sup I here. And then, again, assuming the Markov process is ergodic, the stationary distribution is given by equation A2, where the matrices A sub I star and B sub I star are given by the equation in A1, and this is just the normalizing condition. So now I'm going to turn to some numerical analysis and methods. The key bottleneck in computing the stationary, oh, and by the way, if anybody has questions at any point, please stop me. The key bottleneck in computing the stationary distribution for these structure Markov processes is basically solving for this G min. Once we have G min, we can use the previous theorems to get the stationary distribution. And there's an interesting history here about the most efficient methods to solve for G min. At this point in time, the most efficient methods are based on cyclic reduction. Cyclic reduction was actually first proposed by Busby, Golub, and Nielsen to solve certain numerical solutions of elliptical equations. But then Bini and Meany, being motivated by matrix-analytic methods in queuing theory, they developed various adaptations and extensions of the original cyclic reduction methods for solving Markov chains, and they proved various results. So it is these variants of cyclic reduction that represent the most efficient classical methods for computing the stationary distribution. I'm going to just give you a feel for how the algorithm works, but before I do that, are there any questions? Okay. So the way the algorithm works, and it's sort of this very nice progression. What we want to do, we're going to rewrite this equation here, which characterizes G min. G min is the minimal non-negative solution to this equation. We're going to rewrite it in matrix form this way. And you'll notice the connection between this and lemma, what we saw in lemma A1, and it's exactly the same thing. So what we do is, in the first step, we transform the matrix equation 2 into this semi-infinite linear system where G sup I is G to the power, G min to the power I. Of course, we only care about G min, but that's the expression we have. So in the first iteration, we apply an even-odd permutation to the block rows and the block columns of the expression here. What that does is it gives us, in compact form, the expression in 4, where the U matrices are given here, and B is just what we had on the right-hand side from the lemma. Now, after we do that, I've repeated equation 4 here. This is the one we had on the previous line. What we then do is we apply block Gaussian elimination to this 2x2 block system. And because of the properties of these matrices, which define bounded operators, the one iteration of block Gaussian elimination gives us this compact 2x2 block form. where the matrix H sup 1 is given here in equation 8, and it's actually the Schur complement of I minus U sub 2, 2. The subscript here is different from what we had before with the superscript, sorry. It's indicating the first iteration of block Gaussian elimination. Now, there's some technical details for those that are interested. The inverse of I minus UU and its product with U1, 2 are both block upper triangular toplets. And then multiplying it on the left by U21 is a block Hessenberg matrix. These are important properties that if you're not familiar with it, don't worry about it. Those that are familiar can see that it'll play an important role. So this H1 is block Hessenberg and block toplets, except for its first row, which has a different form here. You see, that's what the hats are representing. And from that, we obtain this expression. So you notice it looks a lot like what we saw before. And in particular, you can observe, and I'll cover this in a little bit more detail in a second, that the expression here in 9 looks a lot like the original expression here we had in 3. And I'll put them side by side in a second. I just want to mention that these matrices, which are now have these superscripts on them for the iteration, A sub I sup 1 and A hat sub I plus 1 sup 1, they get to find an explicit functional form with respect to formal matrix power series. So these are actually growing as the iterations continue. So now putting them side by side, this is the equation from 3, this is the equation from 9. We can see that they all have a very similar structure. And in fact, you can use an inductive argument to show that after n iterations of cyclic reduction, you're going to get something that is of this form. So this is the general form that we have. And you can see that each of these adhere to this general form. Obviously, this is before the iteration. This is the first iteration. This is the nth iteration. And again, these matrices here are, with the superscripts, are fully characterized, are defined by functional forms by means of a recursion and a growing, if you will, formal matrix power series. So if we let pi denote the permutation matrix associated with block even permutations of block Hessenberg matrix H sup n, we get this expression here, where now these are the U matrices, but in the nth iteration. And what happens is the main computational task of cyclic reduction is to compute the first 2 block rows of this matrix, this Schur complement matrix, H sup n plus 1, given here. So this is our goal. And once we have this, what we are able to do is obtain the solution of G min using this expression. This expression converges. The summation here actually asymptotically converges quadratically to 0 as n goes to infinity, and this part here is bounded and quadratically convergent. So there are known convergence results for the method, but it's still, this can take the computation of this H matrix in order to obtain these A's and these G's can be expensive. So this is just, I'm not going to go through detail. What I did want to highlight is this is the classical algorithm. There's an initialization and a test for accuracy, but the workhorse is algorithm C2, which is in fact dealing with the computing this H sup n plus 1 matrix. C2, the bottleneck, not the bottleneck, the workhorses here are algorithm C1 and C4, which are in fact, C3 is actually computing Toeplitz matrix inversion, and C4 is computing a Toeplitz matrix product. So these are the bottlenecks for C2, and it's the algorithm C3 and C4 that we're going to develop quantum algorithms around to speed them up. One can easily show that the computational complexity of the classical cyclic reduction is given by m cubed times d max plus m squared times d max log d max. D max, this is not my New York accent, this is not the max, this is d max, and it's the maximum numerical degrees of power series that are generated as part of cyclic reduction, because you're generating these power series and you're making things larger, and this is the maximum numerical degree of those power series. M, remember, is the size of the A matrices in the definition of the problem. So you can see this can be substantial for large values of M and also large values of D max, but particularly large values of M. The solution involves computations of infinite block triangular Toeplitz matrices, which are approximated by infinite banded Toeplitz matrices, and there are certain parameters that are chosen with respect to these banded Toeplitz matrices that achieve the desired level of accuracy epsilon. This has all been worked out by Beanie and Meany in terms of what these values of D and Q should be to achieve that level of accuracy. So now what our goal is to devise a quantum algorithm that can significantly speed up G-min, the computation of G-min. And again, we're going to be focusing on the C3 and the C4 subroutines. This is computing a Toeplitz linear system and computing Toeplitz products. What we're going to exploit are the properties of Toeplitz matrices and circulant matrices, which I'll talk about in a second, and also the ability to deal with circulant matrices, discrete Fourier transforms, and inverse discrete Fourier transforms on a quantum computer. So now I'm turning to the quantum side of things, coming full circle, but focusing more on the algorithm. I think I've mentioned much of this. I am attempting to come up with ways of speeding up algorithm C3, which deals with Toeplitz linear systems, algorithm C4, which deal with Toeplitz matrix products. Now, the first thing we do is there was work in the preconditioning literature since the late 80s that looked at approximating Toeplitz matrices by what are called circulant matrices, associated circulant matrices. And it turns out that if you have certain properties for the Toeplitz matrices, the circulant matrices will asymptotically become converged to the Toeplitz matrix. So they become a very good approximation for the Toeplitz matrix for sufficiently large Toeplitz matrices. So let me just describe that in a little bit more detail. Let F denote the so-called generating function of a sequence of n by n Toeplitz matrices, T sup n. So n here is our, if you will, the degree of matrix power series, and m is the size of our matrix. So this is something, so m is fixed, of course, but d may be growing. And so we're looking at generating function for the sequence of n by n Toeplitz matrices. It can be shown that these circulant matrices converge superlinearly when f is a positive function in the Wiener algebra class W, and all of these properties hold for our problem. I won't get into, oops. I guess this mentions a little bit about it here. Since P is non-negative stochastic, the Toeplitz matrices have finite sum, and so the associated circulant matrix is an accurate approximation as long as n is sufficiently large. So I'm not going to go through this in detail. Peter Taylor wanted me to, but I'm sorry, Peter, I just don't want to put people to sleep. And I'm trying to wake up those that are already asleep. But the basic idea is you have these n by n Toeplitz matrices, and the entries can be viewed as Fourier coefficients on a certain interval 0 to pi. These generating functions F that I mentioned are what we use to construct the circulant matrix C sup n. We can do that this way. We construct the circulant matrices in this way. You can see it's just dealing with these functions F. The only thing I want to say here is that the eigenvalues of Cn are simply given by these generating functions, and they correspond. The corresponding eigenvectors are the columns of this Fourier matrix phi, and So the matrix operations on the circular matrix have this inverse here, which we can write out explicitly. Again, I just, for those that are familiar with this area, this will make sense. For those that aren't, we're basically just going from Toeplitz matrices to circular matrices because that helps us on the quantum side. Oh, I think I went the wrong way. Did I go the wrong way? Oh, no. So here's the sort of the crux of the, what did I do? Okay. This is all, no, I think I've covered most of this. So here's the algorithm at a very, very high level. We're going to start off by initiating this algorithm Q1 on a digital computer. Then what we're going to do is we're going to operate on two Toeplitz matrices, T1 and T2, and we're going to call algorithm Q2. This algorithm Q2 is executing cyclic reduction. So it's just like C2 was for the classical case. F1 and F2 are the generating functions for those two Toeplitz matrices. We're going to load n columns of the matrix T3 onto the quantum computer to get this state psi 0. And then the important thing is that we can operate on these things in what's called quantum parallel. One of the things about quantum, maybe intuitively you want to think about, is if you were simulating a random walk on a classical computer, you'd start at a state, you'd flip a coin, and you basically follow a sample path on the random walk. On a quantum computer, it can actually simultaneously go across all of those paths in parallel. So there's a tremendous amount of parallelism. So when you see something that's described as in quantum parallel, it's almost as if you can think of the quantum computer having multiple parallel machines that are just operating in parallel and independently. And that's what's happening on each of the n columns of T3. So this is one of the places where we're getting speed up. Then we approximate, you remember what the H function looked like, right? It was the combination of these different U matrices. So we're just adding more of these things in here. And we're taking advantage of Fourier matrices. So I'm not going to get into this level of detail, but we have, this is where the oracles come in. We have oracle access to these generating functions F1 and F2, but these are things that we can compute in a straightforward manner. So we're taking advantage of an oracle, but this is an oracle. Sometimes quantum algorithms take advantage of oracles that nobody knows how to do. This is a case where we know exactly what to do. The next thing we do is we apply quantum Fourier transforms to the columns of T3. We get this psi prime naught state. We're then going to do then we exploit the oracle access to F1 to map this state to this form here that I won't get into. There's something called the HHL approach. It's the first letters of the three authors. It deals with linear systems. It provided exponential speed up, but there were a lot of assumptions and details in there. And we're not using that algorithm, but we're taking advantage of some of the steps that are in that algorithm. In particular, and this might sound odd, adding qubit, okay, fine, a controlled rotation, but then a so-called uncompute operation. And that gives us a state psi 1. And then we're going to repeat this with respect to T2. So we're now going to deal with F2. We're going to apply it to psi 1 prime. We're going to get this mapping, and then we're going to apply the inverse quantum Fourier transform. And this essentially it gives us the result. I know it doesn't seem that way, but the steps are that you just do these operations on these circular matrices, and you apply quantum Fourier transforms, use the oracles, apply, and then at the end you apply the inverse quantum Fourier transform. And now once this is just, I'm going to keep it at a very high level. So this is what actually comes out. At the end, once you've done this enough of times, this is going to become psi star. And so what happens is psi star is computed by this algorithm Q2, and Q1 is going to check the quality. It's essentially going to see if this is sufficiently small. See what this is. This is 1 minus, this is something that we want to basically this product here to be close to 1. So once this is sufficiently small, we know that we've computed it up to epsilon. And these details here I'm going to ignore, but the point is, if the calculated version of this is greater than epsilon, then we repeat, we iterate again. Otherwise, we proceed to output the result, which gives us the G matrix. So this, again, I'm not going to go through this, but this is the algorithm Q1. You can see it looks pretty similar to a great extent from C1. Then the call to algorithm Q2 is more is where the main workhorse is done, where all the things are done. Now, I want to leave 10 minutes for, or at least 10 or 5 minutes for questions. So I'm going to go through the rest of this very quickly. Let me try to give you a high-level view of what we're going to do next. What we're now going to do is analyze the error that we get with this quantum algorithm at each step, and errors are obviously going to accumulate as you iterate through the algorithm. So we're going to analyze that, and we're going to show that one algorithm, we're going to provide an upper bound on the error for one algorithm. Then we can actually create a variant of this algorithm and get an even tighter upper bound, and then we'll get the complexity analysis, which gets into how much better we're doing than in the classical case. But just to set that up, the analysis proceeds along the following lines. There's a pair of matrix functions. These are the things that I didn't describe before, but they define the matrix Hn. These are the things that are actually used in both the classical and the quantum computer. These are the matrix functions that I referred to before. Now, if calligraphy T denotes the transformation that occurs at the n+1st iteration, then what we have is this is the pair that we would have at the n+1st iteration after applying T to what we had at the nth iteration. Then there's T sub f, which is actually, this is the idealized version of the computation. This is what happens when you implement it on a quantum computer, for example. So that the error of a single iteration can be written this way as the difference between the finite implementation and the idealized implementation, if you will. But the pair that you get out of the finite implementation is not going to be the same as what you get out of the idealized. So there's going to be a difference there. So now we're going to use var theta to be essentially what think of the var phi as being the idealized. The var theta is what happens on the real computer. And so one can write expressions for the global error. There's two pieces of this global error. One is the difference between applying the ideal transformation on both the exact and the approximate. The other represents the fidelity of the transformation. So what's going on here? The cyclic reduction algorithm is an approximate algorithm. So you're doing truncation, you're doing of infinite series, you're doing truncation of matrices. There's a lot of different sources of approximation that are going on. The same happens in the quantum side. And so what we're going to analyze, and I'll go through very, very quickly, is bounding that error and understanding that error. Going to skip through all of this. Oh, the only thing I wanted to point out is, as is typically done in this case, we're going to use a first order analysis. And the first thing we're going to do is a first order analysis of the expression in 22, which is this global error that accumulates up to the n+1st iteration. And our first theorem, not going to go into details, but essentially what it does is it provides first order equalities on those errors and first order upper bounds on those errors. Then we actually use that result to get an upper bound on the errors. Sorry, what I said here was these are first order upper bounds on that equation that we had in 22. Key aspects of that. This is actually the upper bound on the errors of the algorithm at the nth iteration. You'll notice they're not that great. They're growing exponentially, but on the classical side, there's lots of it because we have quadratic convergence. The reality is it's probably not exponential, and this is kind of similar to LU decomposition. It's probably not exponential. What's causing us to get an exponential result here is because there's a worst case analysis using the triangle inequality, and that's creating issues. But there is another algorithm that essentially uses what's called a shifting technique. The basic idea is the exact same algorithm we saw before, but instead of applying Q2 to one matrix or one power series, it applies it to a different one. So instead of applying it to this, it applies it to this. I'm not going to go into detail. People that are familiar with this, great. Those that are not, it's just a technique that looks at a different matrix power series, and actually in doing so, you can get linear upper bounds. So you get much better results with this other algorithm. The point is there are these classical results, and we're able to prove the exact same type of results for our quantum algorithms. And this is Q3, this is the new algorithm. The point I wanted to make here is this is exactly Q1, but the only difference is algorithm Q2 is called to apply to a different set of matrices than in the previous algorithm we looked at. Now I'm going to focus the remaining time on the computational complexity. So we went through all of this, and our main purpose was to publish a paper. No, we went through all of this with the main purpose of trying to speed up cyclic reduction. And now the question is, well, what can we say about that? So first, before I get into these details, mu, I'm defining mu to be F1 max divided by F1 min. So this is just a ratio for the generating function F1 that we saw in algorithm Q2. And n sup q is going to be defined here as d sup q max times m. So remember, we talked about d max being the maximum numerical degree of power series. Well, this is the maximum degree of power series for our quantum algorithm. When I use superscript c, it's the maximum numerical degree of matrix power series for the quantum, for the classical algorithm. So our result is here. I'm going to break it down to simplify it, but I just want to point out that one part of this result is that the maximum degree, numerical degree of matrix power series generated by a quantum algorithm is of the exact same order as that for the classical computer. So we haven't changed that. Let's talk about the computation phase. Remember I mentioned before that we have this huge computation space, and then we have an input, a limited input, limited output. Let's just focus on the computation phase for a second. Now, this is what the theorem says. It says that our algorithm is order mu times log squared m d q max plus tau oracle. And that's versus m cubed d max plus m squared d max log d max. Now, what you can show is that if NQ is sufficiently large, remember NQ is this product here. If NQ is sufficiently large, mu is going to be polylog NQ, meaning it's going to be of the same order as this term here. And in fact, for large NQ, mu will be around the condition number of T1. So mu is for the most part in many cases going to be of the same order as this term here. Now, tau oracle, remember I talked about we use some oracles, and so there's a time for that oracle to execute. It is by using, let's see. Well, there are certain oracle methods that we can use, and in fact, in some cases, it's very straightforward for the oracles we're dealing with. So the oracle time can also be polylog NQ, especially for large NQ. So again, this term is also polylog NQ. So under these conditions here, this would all be of order polylog NQ, and this is, well, again, NQ is M times D max, but this is M cubed. So we have a polylog NQ, we're definitely getting an exponential speed up for the computation phase. Now, that's just the computation phase. So there is the input and output, and I'll deal with that in a second, but I do want to make a point. If this calculation of the stationary distribution is sort of part of a larger problem, like solving an optimization problem that involves the stationary distribution, then I don't have any input and output. That's all part of the outer problem that that's using this as, if you will, a subroutine. So if in fact, we're going to get to input output, I'm not cheating, but I'm just saying that in some cases, if this is a core subroutine of a larger problem, then in fact we are getting exponential speed up for this core part of the problem. And there are very few problems for which one has exponential speed up. So now, input phase. Let's talk a little bit about the input phase. What happens here is, this is the mu, this is the log, and this is the tau oracle. The additional is the tau load. It's the time to load the problem into the quantum computer. Now, there are methods called block encoding, quantum circuit methods. A lot of work has actually been done, really great work by Lin and other folks in the area, that have come up with ways in which you can use block encoding to efficiently load these matrices into the system. So if we're able to take advantage of this, as well as the properties of these matrices, such that tau load is polylog, then we would have the same thing we had the previous one, an exponential speed up, or even if it's sub-exponential in log n, then we would actually have a polynomial improvement over the classical method. And lastly, on the output. So again, the way this algorithm would run is you would run the system and you would sample and you'd get one element of the G matrix. You're not going to get the whole G matrix. So in some sense, what you would need to do is you would need to have the G matrix be sufficiently sparse in order for the output to be log n, or a polylog n, or sub-exponential in log n. Of course, one might actually not need to use the entire G matrix, maybe because of structural properties, there's certain parts you could focus on. But on the readout side, you would need additional properties for the output, the sampling-based methods on the output to give you the result that you needed. And then in that case, you would, but again, this is the readout that gets added to it. And I think, in summary, we tried to compute the stationary distribution. We devised quantum algorithms to do it. We analyzed it mathematically. And again, I think it is an important role for this to play a subroutine as opposed to focusing just on the input and output. And let me stop there, and I think I went a little longer than I should have, but thank you very much.